Okay, welcome group. This lesson is going to touch on an atomic theory that adds to our understanding of the atom. And just at the outset here, I'm just focusing on just a picture of what's called a line spectra, or line spectrum in this case. And I've got a couple questions here. What are we looking at? How is it produced and why is it produced? And this is what Niels Bohr was working on when he came up with his theory of the atom. And he was dealing with the element hydrogen. He was burning the gas. He was passing the light that was emitted from the burning of this gas through a prism, and he was collecting that uh, sort of fingerprint of the element onto a plate and observing the different colored lines. And the why was his quest afterwards. And so that's sort of what we're going to look at in this lesson is why do these colored lines appear and why do they differ from element to element? Here is a very colorful chart of line spectra of various elements. And they run vertically, but usually scientists view them horizontally. And then when you look at all this, it just looks like colors, and you see lots of different colors of the rainbow. But you do see that in some cases elements have very few lines on their line spectrum, and others have quite a few. And the intensity of the lines can even differ even for the same color. So we want to understand what was going on here. And that's what Niels Bohr started with, is the line spectra of hydrogen. And the theory that he generated uh, goes a little bit something like this. He understood that the atom was consisting of subatomic particles. The nucleus was understood to be a dense positive core, and he hypothesized that these electrons occupy certain orbits or certain shells or energy levels. And in his model for hydrogen, he numbered them from 1 up, and he supposed that when hydrogen was energized and burned, that the electrons in the atoms were gaining what he called a quantum of energy, or a small amount of energy. And when this transition occurred, there was a reverse process which was possible. And when that electron returned to its natural state, it emitted a photon of light, which has a certain color. And I assume he understood the physics of light and that the different colors of light correspond to different energies. And so all the possible transitions that a hydrogen atom can undergo with its single electron, each of those, depending on how much energy the electron absorbed and re-emitted, that transition would generate a certain frequency of light, or a certain color of light. And that some with higher energies would emit purple light, and some transitions that only involve small amount of energies would produce, say, red light. And the intensity of those bands of color on the line spectrum must have corresponded to how often those transitions were occurring. So let's start to fill in your note here. You have a package in your handout. Should look like this. I'm just going to go through and reveal some points as we get along here, and you can fill in your note. So according to his theory, electrons in an atom possess only specific energies called energy levels. That's his first postulate, or first point. We understand this when we draw Bohr diagrams, that the path of an electron is called its orbit, and we sometimes talk about the outer orbit, valence electrons. And we pretty much just draw it as a circle, almost the way planets would orbit around the sun. And we don't really try to show any detail in this orbit, aside from just it gets further and further away from the nucleus. Now, I talked about this when we showed the visual of these transitions, that there's natural position of an electron, and it's going to correspond to the energy level that it naturally occupies. So that's called its ground state. Now, an element that has more than one electron, which is anything except hydrogen, could have possibly many ground states, depending on how many energy levels are occupied. There could be a ground state for the first energy level, a ground state for the second energy level, and as more electrons are added into larger and larger atoms, there will be more ground states possible. Now, when electrons move between these energy levels, this is called a transition. Let's have a look at that.
According to the Bohr model, when a hydrogen atom receives energy, its electron leaps from a low-energy orbit to a higher one, forming an excited state. As the atom loses energy, the electron jumps back to a lower energy orbit, releasing light as it goes. When gaining energy, the orbit to which the electron jumps depends on the amount of energy involved. When the electron occupies the lowest energy orbit possible, the atom is said to be in the ground state.
All right, so let's add a little bit more to our note. Energy, when electrons move or transit to a higher energy level, that requires an absorption of energy from the surroundings. So it could be heating the sample, it could be passing electrical current through a gas, maybe even shining some kind of radiation on the sample might be enough to energize it. And when it does so, it moves to what was called an excited state. So an absorption of energy is required. And then when the electron returns to the ground state or a lower energy level, energy will be released. And of course, there's some natural applications for this. Okay, fireworks, of course, is one. Different compounds contain different elements, and those elements have different electron configurations, and the transitions from ground state to excited state and back correspond to different colors of light given off. Another one would be the identification of an unknown substance.
If we pour methanol onto sodium chloride and ignite it, the flame produced is yellow in color. If instead of using sodium chloride we use boric acid, a compound made of boron, hydrogen, and oxygen, the flame produced is green in color. Each salt imparts a characteristic color. The emission of light by heated or burning objects provide important clues to our understanding of atoms.
All right, and this can be used in a field of chemistry called qualitative analysis, where we're more interested in what is being analyzed and not how much. And qualitative analysis is a little bit like DNA fingerprinting. We can identify who was at the crime scene because we have a sample of their DNA. So if we have a sample of the fingerprint of an element, we can identify it. And this, of course, is what's done when astronomers look at stars, as they know the fingerprint of different elements that they've studied on Earth. And if they see that characteristic fingerprint pattern, then they can infer that the element must be present in the burning star. Of course, what they're looking at is a line spectrum, and that's simply a pattern which includes all of the different excited state to ground state emissions of light energy from those transitions. Now, the next thing we need to understand about light, of course, is that light exists as photons, and these are particle-like in their nature. They behave a little bit like particles, but they also travel in waves. And light is an electromagnetic wave. And visible light is just one form of the electromagnetic spectrum. I'll show a little simulation here to help you appreciate the relationship between the wavelength of light and the color of light. So those wavelengths, if you can imagine water moving in waves, so the longer wavelengths, which is defined as the distance from a crest to a crest, or the low trough to the next low trough, that's the wavelength. Longer wavelengths have lower energy, and those would be colors towards the red end of the visible spectrum. Those with higher energy have shorter wavelengths, and there's an inverse relationship, as you can see, that the wavelength and the energy are inversely connected. In this little simulation, you're just going to see the wavelength of light change just very subtly, and as you do, you'll see the color of the wave change as well. So that's just not extremely accurate in that we don't really see waves quite the same as we see water waves. However, it just does convey that relationship that I referred to before. So wavelength in physics is given a Greek letter lambda, so you'll see it at the top. That's the crest to crest distance. It's measured in nanometers, which is a billionth of a meter. Okay, so you have nine decimal places in your value, and they all follow after 0 dot. So very, very small lengths we're dealing with here. So the light was purple, and then it was blue, and now as the waves get longer, we're getting into the green, yellow, orange, and then eventually the red wavelengths. So the Bohr model, just to sum up, Niels Bohr 1921, we're looking at specific numbers of electrons in quantized energy levels. That is, the locations where these electrons are, only specific energies are permitted, if we could say. And we know that because only specific colors of light are generated when electrons undergo these transitions. It explains the periodic law. The periodic law is that when elements are arranged according to increasing atomic number, we will get periodic or regularly repeating properties. And that is that group 1 elements, for example, have similar chemical reactivity. Group 8 elements, the noble gases rather, are unreactive, and the similarities of line spectra also supports this periodic law. Let's have a look at this practice worksheet that you have in your package, which is electron energy level diagrams for atoms. So we're using the Bohr model of the atom based on electron filling, and simply we're just putting the symbol at the bottom. One is shown for us there with aluminum. Hydrogen has 1 proton, and that's in the nucleus, and then above that we have the first energy level, which would be 1 electron. So that would be the simplest energy level diagram that we could draw for an atom. If we were to choose something with more electrons, for example, beryllium. Beryllium has 3 electrons, and it has 3 protons. So the convention is line sort of separates the nuclear particles from the orbits, and then we would have 2 electrons in the first, and then 1 electron in the second energy level. Okay, so we can complete that, and it gives us an understanding of the way these electrons are ordered or stacked. Now, maybe the one misconception is that it could create is that the electrons are necessarily further away from the nucleus. So I just want to touch on the quantum theory just to give you maybe a different idea of a fuller understanding of the atom.
A familiar depiction of the atom shows electrons orbiting the nucleus like planets around the sun. This model is neither accurate nor useful. We no longer think of electrons as orbiting the nucleus, and we cannot predict their location with accuracy. A more useful model is the quantum mechanical view of the atom, which represents the positions of electrons in terms of their probability of being in a particular region around the nucleus. If we could show all positions for an electron with a specific quantized energy, the resulting picture would look something like a cloud.
So here you're seeing 5 different elements and their electron clouds, which, as was mentioned in the previous animation, really is just a mathematical probability of finding an electron in a particular location. But if we consider all the possible locations, it gives us a sort of 3-dimensional space that the atom occupies, which is very realistic, of course, because we know that matter occupies space. So here would be sodium, mercury, silicon, nitrogen, and neon. You notice that the size of electron clouds varies as we move through those, and we'll look at periodic trends as well in this chapter, and we'll be able to explain why the size of the atom or its radius changes as we move along the period or down a group. Okay, so to wrap up, the final point here is that there is a more accurate, I don't entirely agree with her comment that it's a useless model, but it's not as useful, that the quantum theory is more accurate at modeling the position and energy of electrons relative to locations that in three dimensionals we would call an orbital. And if we just look at the quantum mechanical theory, just sort of summed up, here's some of the names that were involved, Schrodinger and Heisenberg. And this was a little bit later on, born in 1921, so still in the 1920s, electrons in probability orbitals or wave patterns. We'll look at this a little bit more in the 4U course as well when we look at quantum numbers. Okay, so just in closing here in class, you'll have an opportunity to view some line spectra of different elements, and you'll have an opportunity to look at the difference between line spectrum and continuous spectrum, which we would observe for sunlight or something maybe similar to it in the fluorescent tubes in the classroom. We'll complete the worksheet for the energy level diagrams. We're going to do some activities in this section. We're going to be looking at burning elements and using the Bunsen burner to produce flames of different colors, and how we can use that to qualitatively identify an unknown. And the questions that we're going to be working on in the textbook, once we've looked at all the different ideas in this section, are found on pages 42 and 45, 1 to 8. I'll see you in class tomorrow.